Now, we have interpreted tau in terms of molecular momentum flux. What are the advantages? What are the limitations? That is a discussion now. First major advantage is that you can explain fluid flow from a molecular point of view. This does not mean that we are the explanation is from molecular point of view. This does not mean that we are going to the molecular level of description. Remember, we said transfer phenomena can be transfer phenomena can be discussed at 3 scales or 3 levels: macroscopic, microscopic and molecular. The first statement does not mean that we are discussing at the molecular level, only the molecular interpretation can be given. Still we are in the continuum hypothesis only. So, explain fluid flow from a molecular point of view. Now, this of course we can appreciate the second bullet after discussing energy transport and then species mass transport, but still we can explain momentum transport analogous to energy and species mass transport based on the molecular transport mechanism. We are talking in terms of molecules moving, transporting momentum. The same molecules can transport energy, can transport species mass. So, we can explain the the momentum transport analogous to energy and species mass transport based on the molecular transport mechanism, okay. Or the transport of momentum, energy and species mass all can be explained using a molecular mechanism, okay. Because we are able to explain the transport of momentum, energy and species analogously through the molecular mechanism, it also helps us to understand the analogy between the molecular transport of momentum, energy and species mass. Because our explanation is common, we can understand our explanation using molecular mechanism is same, we can understand, it helps us to understand the analogy between the molecular transport of momentum, energy and species mass. What does it mean? We have seen our momentum flux is proportional to negative velocity gradient, or in general when we generalize, we can generalize it saying as flux proportional to negative of gradient. What does it mean? For the present case, the momentum flux or molecular momentum flux is proportional to the negative of velocity gradient. Of course, in terms of equation it becomes minus mu dou Vx by dou y. Later on we will see that the heat flux, or let us say molecular heat flux, is also proportional to the negative of temperature gradient, and the equation is minus k dou T by dou y, which we call as the Fourier's law of heat conduction. Still later on we will see that the molecular species mass flux is proportional to the negative of the mass concentration gradient, and the equation is minus dAB dou rho A by dou y. K is thermal conductivity and dAB is the diffusivity, and so all the molecular fluxes are proportional to the respective gradients, and all of them have the negative sign as well, okay. Suppose if we had a positive sign here which was based on our old fluid mechanics convention, this analogy becomes difficult, okay. Of course, we also interpreted tau as viscous stress, we would not be able to look at this analogy, because we came to momentum transport and changed our viewpoint of tau as molecular momentum flux. We are able to look at this analogy. If we interpret tau as viscous stress, then this analogy is not possible. If we interpret, because we interpreted tau as molecular momentum flux, this analogy between molecular momentum flux, molecular heat flux and molecular species mass flux is possible. All of them have similar looking equation. Of course, this we will call it as a Fick's law of diffusion, okay. So, in terms of the transported quantity, it is momentum, heat, species, mass, of course the molecular momentum, heat, species, mass flux, and they are all proportional correspondingly to the velocity, temperature, concentration gradient. Concentration here we used mass concentration. Okay. What is the other advantage? So far we had tau on the right hand side expressing as a viscous stress. Because we brought it to the left hand side and then interpreted as a molecular momentum flux, this viewpoint enables us to sum the convective momentum flux and molecular momentum flux and look upon as a total momentum flux. So, we can now say that we have a total momentum flux that has a convective contribution and a molecular contribution. So, that is why this equation is written as total momentum flux is equal to convective momentum flux plus the molecular momentum flux. And this representation of total momentum in terms of convective momentum and molecular momentum also analogously carries on to energy transport and species transport as well. Okay. So, this viewpoint once again establishes the analogy. Okay. Now, so far we have been interpreting tau as stress, which is force per area, certainly more easily visualizable than when I say molecular momentum flux. When I say tau as stress and force per area, force we can measure directly or indirectly. So, we can relatively easily you can visualize stress compared to molecular momentum flux, certainly much more easily. Both are in fact difficult to visualize. On a relative scale, when you say stress and force per area, at least force we have we can measure in a lab. So, relatively easy to visualize compared to a term called molecular momentum flux. Okay. Now, once again this we may not appreciate until we go to energy balance, and then we may not also include this, but to have when we will understand this later on in maybe an advanced course. This interpreting tau as a viscous stress is required when you go to energy balance. Why is that? When you go to energy balance, we will include work done by body forces, work done by surface forces. Surface forces are pressure and then viscous stresses. So, what we do there is, or what we include there is, we say work done by, or rate of work done by pressure, rate of work done by viscous stresses. We do not say rate of work done by molecular momentum flux, that interpretation is not useful there. So, there when we go to energy balance and include this work done by viscous stresses, this mechanics viewpoint is certainly required there, we cannot avoid that viewpoint. So, though in terms of fluid flow we can either take a viewpoint as stress or momentum transport, when we go to energy balance and want to include the work done by the viscous forces, the viscous stress viewpoint will be required. We cannot interpret as work done by molecular momentum flux. Okay. That is one of the limitations. Okay. Now, this again is a limitation which at this introductory level we will not be able to appreciate and realize, but if you take a advanced fluid mechanics course, or if you are doing research in fluid mechanics, this third bullet plays a very major role. If you want to solve and analyze more advanced fluid mechanics problem, when I say more advanced fluid mechanics problem, these are problems I would say at a graduate level or research level, at a postgraduate level or research level. So, those problems are all solved only based on the viscous stress viewpoint. It is very difficult to solve those problems extending the molecular momentum flux viewpoint. Okay. It helped us to explain from a fluid flow from a molecular viewpoint, but to extend that and solve more involved problems is difficult, and only the viscous stress point will help us to solve such kind of problems. Okay. Most of the problems we talk about the flow field and then the force, resulting force or the force causing it, etc. So, we always talk in terms of the viscous force only. Okay. Okay. The other limitation is that the viscous stress interpretation is more universally followed. The molecular momentum flux interpretation, I would say, is more popular among chemical engineering field, chemical engineering discipline, but if you look at other disciplines or other engineering disciplines, be it mechanical, civil, aerospace, ocean engineering, the viscous stress interpretation is what is followed. So, in that way the viscous stress interpretation is more universal. Okay. And so, these are some of the limitations of interpreting tau as molecular momentum flux. Okay. Now, the question arises, what is the scope of this lecture for this course? Why did we discuss this dual viewpoint? What is the need for this lecture at all? Okay. First, the scope of the course determined this lecture. I would say this is a unique lecture for this course. The scope of the course wanted us to look fluid flow from a mechanics viewpoint, because we had continuum mechanics. The course also had transfer phenomena. So, we need to look fluid flow from a momentum transport viewpoint, which means that we should look from a molecular momentum flux viewpoint. That is why in this particular course we have this lecture where we try to connect both these viewpoints. Okay. So, to put it down here, continuum mechanics where we viewed as viscous stress or a force viewpoint, and transfer phenomena we viewed as a molecular momentum flux or a flow viewpoint. Okay. That is why this is required. Suppose if we have a course only on, let us say, continuum mechanics or fluid mechanics, we would just stop with interpretation as viscous stress only. Suppose we have a transfer phenomena course, we would just stop interpreting as molecular momentum flux. But because we are including both in this course and we need to connect, and that is why we are discussing this. Okay. Also, you would have had a course, or you would be taking a fluid mechanics course in let us say 3rd or 4th semester, where the tau will be viewed as viscous stress or force. Then you would take a transfer phenomena course, let us say in 6th semester, 7th semester, the course name will be transfer phenomena, the book name also may be transfer phenomena, where you will view tau as molecular momentum flux. And what we have done here is to connect, and let us say when you go later on to energy transport, once again you will view tau as viscous stress or a force. What we have done today is to connect all this, whatever you would come across in different courses in different parts of the course. A mechanics viewpoint in fluid mechanics course, a momentum flux viewpoint in momentum transport, once again a viscous stress viewpoint in energy transport. Okay. So, we are this idea of this lecture is specifically keeping these in mind, so that you have a better idea of the two different viewpoints. Okay. So, let us summarize this unique lecture. Tau can be interpreted as viscous stress, that is a fluid mechanics viewpoint. Molecular momentum flux, that is a momentum transport viewpoint. Okay. I think that is the bottom line for the entire lecture. Both the expressions for tau can be reconciled if the sign convention for stress is suitably changed. We have discussed that. What is the consequence? There is a sign change in the Newton's law of viscosity. And what happens in the linear momentum balance? We consider tau as a molecular momentum flow or a flux on the left hand side rather than surface force on the right hand side. What happens because of that? Sign change for the terms with tau, okay. All other terms of course remain same. So, fluid mechanics, it was net viscous forces on the fluid on the right hand side, and if you keep it still on the right hand side, it becomes net rate of flow of momentum entering by molecular transport. If it is on the left hand side, it is leaving; if it is on the right hand side, it is negative sign, and so it is entering. So, net viscous forces on fluid on the right hand side, that is a fluid mechanics viewpoint. 2, net rate of flow of momentum entering by molecular transport, once again on the right hand side, that is a momentum transport viewpoint. What happens with the Navier-Stokes? Sign changes cancel, okay, and no change in equation. Okay. And we also discussed the advantages and limitations of the molecular momentum flux interpretation.